Chapter 5, Section 9, Operations with Complex Numbers. This is the last section in Chapter 5, and I think it also might be the easiest. So far, what we know about complex numbers is that we can get them as an answer to a quadratic. But that's all that we've done. We've gotten them as an answer, and that's been it. And so today we're going to look to see how we can do some operations with them. Some learning targets for today. I can graph complex numbers. Yes, we are going to graph these on a number line. I can find the absolute values of complex numbers. I can reduce powers of I. That's probably the most tricky. I can add, subtract, multiply, and divide complex numbers. And so, to graph complex numbers, as I mentioned, we're going to graph these on a number line. And so we just have our regular number line. Well, that's the real number line. We have an imaginary number line as well that goes perpendicular to that. And they cross at where they both equal 0. Now this looks kind of like the coordinate plane, what we are used to graphing on when we have points. It's not exactly the coordinate plane, but pretty much, yes it is. It behaves just like it. It's actually just a number line, however. And so, let's look at a bigger one with some numbers that we can actually graph on. And let's graph some points. Let's graph the point 7 minus 2i. So if we start our point out at the origin at 0, 0, well at 0 plus 0, I, we're going to go 7 in the real direction. So we can slide it over there. And then we're going to go negative 2 in the imaginary direction. And so we slide it right down there. And you might be thinking, wow, that looks like the point 7 comma negative 2. It's true. It does look like the point 7 comma negative 2. It's not the point 7 negative 2. This, again, it looks like it. It's not. It behaves just like it. If you have to graph an imaginary number, yeah, you can graph it as like 7 comma negative 2, and you'll get exactly the right answer. But technically, it's not. It's a distinction without a difference, or a difference without a distinction. It's one of those. It's not exact. It's not the same, but for all intents and purposes, it looks the same. So, keeping in mind that 7 minus 2i is basically graphing the point 7 comma negative 2, try these couple. Now, by the time you pause this, you should probably have these already graphed by now. So, but if not, go ahead, hit pause, and push play again in a couple seconds. Easy? Let's see, negative 4 plus I. That'll be backwards 4 up 1, because that's plus 1i. And so then 2 minus 3i over 2, down 3. And we have these points. It's pretty easy, yes? When you're doing these on your homework, you can put them on the same graph. Just make sure you label which one's which. I labeled mine via color, but you could put negative 4 plus I by the blue one, 2 minus 3i by the green one. That way you don't have to make these number lines for every single problem. So that's our first topic. Second one, absolute values of complex numbers. So what is an absolute value? Most people think, oh, an absolute value, just make it positive. If that's what you're thinking, no, you don't just make it positive. Think back to when you first learned about an absolute value. What is an absolute value? It's the distance from 0. Now, on just a regular number line, that distance is the same as the value, only it's positive. However, when we have something like 7 minus 2i, which is the same one we just looked at, it's not on the number line. It's way down below the number line. And so, the distance from here to 0 is this diagonal distance. Well, how could we possibly find that? Well, if in doubt, draw a picture. In this case, our picture would probably look like a triangle. We have a side length here, which is 7, and we have a side length here, which is 2. Well, this is a right triangle, so we can use our Pythagorean theorem. we're going to do 7 squared plus 2 squared to equal the hypotenuse squared, and we can just take the square root. So the absolute value of this will be the square root of this squared plus this squared. And so 7 squared is 49, 2 squared is 4, add them together, we get the square root of 53. It's very possible we'll be able to simplify that, but not in this case. But here, the absolute value of 7 minus 2i is the square root of 53. And all it is Pythagorean theorem, which is just a distance formula, by the way. So let's look in general. What is this? Because that's just for that specific case. In general, if we have a plus bi, it's just a squared plus b squared, and then square root. So that's a nice little quick, easy formula that, again, notice Pythagorean theorem or distance formula. That's all that is. But you can solve that without having to draw a picture. Notice the I is not included in this. We don't square the I. It's just that b, the imaginary part. So, keeping that in mind, try these couple. We have the absolute value of 4 minus 3i, the absolute value of 7i, and the absolute value of negative 2. So go ahead and push pause, try these, and then come back in a minute when you think you have them. How was that? So the first one's going to match the formula perfectly. Just plug it in, 4 squared plus negative 3 squared. 4 squared is 16, negative 3 squared is 9. Remember, it will be positive. 16 plus 9 is going to be square root of 25, and square root of 25 is 5. And so the absolute value of 4 minus 3i is 5. And then, how about 7i? The absolute value of 7i. Well, this is going straight up 7. The distance is just a straight line. This absolute value is just going to be 7. If we plugged into the formula, we'd have 0 squared plus 7 squared. It's 49, then square root gets us right back to 7. So that's really easy. If it doesn't have a real part, just take the number and make it positive. How about negative 2? The absolute value of negative 2. You know what the absolute value of negative 2 is. You've known that for years. Don't get confused by this. It's still just 2. It's the distance from 0. It's straight horizontal. Negative 2 squared is 4, plus 0 squared is still 4. Square root is 2. So really the only time you have to worry about it is when you have both a real and an imaginary part in your complex number. So how are those? Pretty easy still? I hope so. Powers of I. Again, this is possibly the most confusing but not hard. So we're going to look at what is I. Remember that I is the square root of negative 1. I know I have another extra equals I here just because we're going to develop a pattern. So that's why that's there. It's repetitive, I get it. So I is the square root of negative 1. Well, what happens if we square that? When you square something, you square a square root, you just get what's inside of it. So the square root of negative 1 squared is just negative 1. And you might be thinking, no, because I have told you that when you square something, it's always going to be positive. Yeah, well, we simplified. When you square a real number, it will be positive. If you square I, you'll get negative 1. Remember, I is not a real number. The rules don't apply the same. So, we have negative 1. What if we do I cubed? Well, that's just multiplying I to it. Negative 1 times I is negative I. How about I to the 4th? Let's multiply I again. That'll be negative I squared. I squared is negative 1, so we have negative 1 or positive 1. What if we do I to the 5th? Well, 1 times I is going to be I. Well, I to the 6th. 1 times, so I times another I is I squared, which is negative 1. I to the 7th, multiply by an I to the 8th, multiply by an I again. Are you starting to see a pattern develop here? I hope so, because there is a pattern here. And what you should be seeing is this is going to be one of 4 things. It's going to be either I, -1, -I, or 1. And that pattern is just going to keep repeating over and over and over again. And so if you have an I with an exponent, how do you figure out where on the pattern you are? Well, the easiest way is to look at the ones. Because if you notice the ones, that would be I to the 4th, I to the 8th, I to the 12th. If it's a power, or not a power, if it's a multiple of 4, the exponent's a multiple of 4, it will be 1. And then you just need to figure out how far off of that are. So if we look at, say, I to the 83, we'd think, all right, so what is close to 83 that's divisible by 4? Well, that'd be I to the 80. So we could rewrite this as I to the 80 plus 3. I to the 80 is going to be 1. Then we just need to go 3 more places. It's basically I to the 6, or it could be the same as I cubed, which is just negative I. Not I to the 6, I to the 7. 1, 1, 2, 3. So it's the same as I cubed, which is -1. So we could start out at any place where we have 1, I to the 4th, I to the 8th, then we just go up 3 more places, or up in the pattern, which is down, and we get -I. How about something with a number in front? 2 times I to the 15th. Well, I to the 15th is going to be either positive or negative 1 or I, multiplied by the 2. Well, what number is 15 close to that's divisible by 4? You might think 12. All right, it's 12 plus 3. Maybe instead of 12, it's 16. 16 minus 1. Well, I to the 16th is going to be that 1. And we just need to go backwards 1 to get to -I. 2 times -I is -2I. All right, so try these real quick. We have I to the 102nd and -3I to the 21st. Go ahead, pause, and come back when you're ready. All right, how are these? Let's see, 102. I'd say that's probably 100 plus 2. 100 is going to give us 1, so we have I squared, which is just -1. I to the 21, well, 21 is 20 plus 1, which is just going to give us I to the 1st, which is I, so we just have -3 times I is -3I. Right, so now we can look at, so that was that topic. Now let's look at some operations. And with operations, these i's can be treated pretty much like a variable. There is one small difference, and that's that I squared equals -1. Other than that, we can treat them just like variables, just like if it was an x. So looking at addition and subtraction, we're going to combine like terms. And so, if we have something like -1 minus 8i plus 4 plus 3i, combine like terms. We're going to look at the real part, -1, 4, and the imaginary part, -8i plus 3i. -1 plus 4 is 3. -8 plus 3 is -5, so we have 3 minus 5i, just like if those were x's. Subtraction is going to be the same, with the difference of we have to make sure that we distribute that minus sign. This is going to be 1 minus 3i minus 7 minus I. Then combine our like terms. 1 minus 7 is -6. -3i minus I is -4i. So addition and subtraction, combine like terms. That should be one of the easier ones. For multiplication, we're going to have to distribute. So if you have something like 9 plus I times 4 minus I, you're going to have to multiply 9 times 4, 9 times I times 4, and I times -I, just like if those were x's. 9 times 4 is 36. Then we have minus 9i plus 4i minus I squared. The minus I squared is -1. And so minus -1 just turns into +1. Combine like terms, 36 plus 1 is 37. -9i plus 4i is -5i. So we have 37 minus 5i. If we have something like 2 plus I squared, remember when you square something that's not 2 squared plus I squared, we have to distribute, just like we did with the one above. So we're going to have 2 times 2 is 4, 2 times I is 2I, plus another 2 times I is 2I, plus I squared. So we have to distribute those. The I squared is just minus 1. 4 minus 1 is 3. 2I plus 2I is 4I. So we have 3 plus 4I. Then division. Division is a little bit different. We have right as a fraction, and then to divide, we're just going to realize the denominator. It's kind of like rationalizing the denominator with square roots, only we're going to make them real. To do that, we're going to multiply the denominator by the complex conjugate. Just change the sign of the imaginary part and multiply. Now we can't just multiply the denominator by whatever we feel like that. You have to do the same thing to the numerator. So this division problem just became 2 multiplication problems. So let's do this. Let's take a look at the denominator first. When we distribute this denominator, we're going to have 2 times 2 is 4, then 2 times 4i is 8i, then minus 8i, minus 16i squared. Well, notice that plus 8i minus 8i is going to go away. That's what multiplying by a conjugate does. The minus 16i squared, I squared is negative 1, so that just changes into plus 16. Combine, 4 plus 16 is 20. The 8i's go away, and so we get just 20. If we look at the numerator, we can distribute 11 times 2 is 22, and then plus 44i minus 10i plus 20i squared. Well, that I squared changes to plus negative 1, which makes it plus 20. Combine like terms, we get 44 plus 34i. It is more appropriate to split these apart into 2 fractions. It also makes it easier to simplify. So 44 over 20, we can divide by 4, we get 11 over 5, plus 34 over 20, divide by 2, 17 over 10i. So let's try a few of these. We have a subtraction problem, an addition problem, a multiplication problem, and a division problem. Go ahead and take a few minutes to try these. The first 2 should be really quick. The second 2 may be a little bit longer. But then push pause, come back when you're done. All right, so looking at this subtraction, first we want to distribute that negative. Then we can combine like terms. 8 plus 2 is 10. Negative 9 plus 1 is negative 8i. Addition, don't even need to distribute. 4 minus 9 is negative 5. Minus 7i. The squared one, remember we need to distribute that. When we do, we get 25 plus 30i plus 30i plus 36i squared. The I squared changes to negative 1, makes that minus 36. Combine like terms, negative 11 plus 60i. And then division, multiply by the complex conjugate. 3 minus I, same thing to the top. We can multiply each of them. The I squareds become negative 1s. Then we can combine our like terms, so we get 13 minus 11i divided by 10. So that was operations with complex numbers. That's a lot of topics, but a lot of them are really easy. We're spending 2 days on this. I will see you in class, ready to do a quick group activity.